In this example, I want to discuss a few Verilog HDL concepts using an example I've created in the ISC Webpack. This particular module you see in front of you is meant to represent an 8x1 multiplexer. Now there are multiple ways to do this in Verilog HDL. This is just one example. And a lot of the options have been chosen based on things I want to demonstrate. So you can find smaller implementations of this online. First, when you look at Verilog HDL, everything's broken down into modules. Although there are a lot of similarities between Verilog HDL and C, there are some differences as well. Everything ends in a semicolon. Comments look the same, but the syntax and how it works can be very different. Let's start at the top. With the first line, declaring the name of the module as well as the ports, the inputs and outputs, we see here that the name of this module is Mux8x1, and the ports are called selection bits, D0, D1, D2, D3, D4, D5, D6, D7, and F. Just below the module declaration, you have a list of the inputs and outputs. These are really just the ports listed in the initial line. However, they can be defined a little bit more explicitly. For example, selection bits is really a 3-bit value. The line right under the module line, beginning with the word input, showing the 2:0 in square brackets, indicates that selection bits is a 3-bit value. The 0 is the low order bit, the 2 is the high order bit. 0, 1, and 2 are the 3 bits. This allows us to access them later on, should we choose, using array style notation. We also label D0 through D7 as inputs, and we label F as our output. And notice right below that we declare a reg for F. We do that so that F can store its value long term. An alternative would be the use of the word wire instead of reg. These do not maintain their state over time and are normally used just as a means of connecting gates together. I'm going to scroll down just a bit here so that we can see the remainder of the module. The biggest part of the remainder of the module is this always block. The always block is meant to indicate the conditions upon which the code within will be executed. In this example, we will always execute the code within when the particular condition is true. In this case, where there are changes to any of the inputs, the selection bits, or any of the D values. And each of the D values is 1 bit. When something changes with any of those, the code between begin and end will be executed. And really the purpose of this code is to simulate a multiplexer. So when something changes, we check the selection bit sequence. This determines which pin is allowed to pass through. Now if you look at the case statement, which is very similar to what you may have seen in C++ as a switch statement or a cascading if, we look at the selection bits and try and find a matching value. The syntax here may look a bit strange. For each of the cases, we begin with the number 3, followed by an apostrophe, followed by B, and then 3-bit values. What this is saying is we want to check for a sequence of 3 bits, starting at 0, 0, 0, and going up from there. If any of these patterns match the selection bits, the value of F is then set to be one of the D bits, or specifically one of the input bits. Notice here for assignment we're using a less than symbol and an equal sign. This is a non-blocking assignment. If, for any case, we had multiple assignment statements, a non-blocking assignment would mean that those assignments happen in parallel, which is often the case with hardware. However, here we only have one assignment for any given case. So it's really not necessary per se, but it's mainly here for demonstration purposes. There is a default case here where F gets set to 0 if there is an undefined sequence. And of course this should not happen but again, we added it here for demonstration. So anytime the selection bits or the input lines change, this block of code will be executed. In other words, the selection bits will be checked and something will be sent out over the F output. This is an 8x1 multiplexer as implemented in Verilog HDL. Let's take a look at a test bench for such a thing. I'm going to scroll this down a bit, but here's an example test bench. And again, this may be overkill, but I really just want to demonstrate a few things. With a test bench, most of the code in the beginning at least is auto-generated. When you create a test bench in the ISC Webpack, it asks you what you're trying to test, and then it generates some code to help you do that. You can think of it this way. It creates a Mux8x1 instance called UUT. UUT is short for the unit under test. It ties in to the inputs and to the output differing regs and wires defined above. There's also some variables here that I created that are integers, simple integer variables you can think of them as. And I've created 3 bit streams, A, B, and C, A bit stream, B bit stream, C bit stream, which are 16 bits long. Now the reason for doing this is because I want to generate a table of values to show what the mux will produce given different values of the input and the selection lines. Now in a test bench, often you see the term initial. Initial usually followed by begin and end, depending on how long the code is. But initial blocks will happen when the test bench runs in parallel, so you can have multiple initial blocks. Here we have one starting at the top as I scroll down. And this one's fairly long, and we'll get to parts of it here in a moment. But at the very end, there's another initial block. It says initial, #500, and then $finish. What this means is both initial blocks will happen in parallel, but the second one says that after 500 time units, the simulation should end. This is our trigger, if you will, to have the simulation end at a defined time. So let's take a look at what's going on with the other initial block. Now a lot of what's in this initial block is setup. Really what I'm doing is I'm filling 3 bit streams so that I can generate this table showing the different 3 bits for the selection bits, as well as the values that come out on the other side with F. Now you see for loops here, which look very much like C++. Now these for loops here in the beginning are just used to fill up the A, the B, and the C bit stream. The details there aren't important. What comes next, though, is where we initialize a few things. We initialize the data lines D0 through D7, which are defined as reg in this particular side of the equation. And I also have A, B, C, and D, which I also initialize to 0. The #100 means wait for 100, I should say time units there, it's not necessarily nanoseconds, for the global reset to finish. Now what follows are assignment statements, but they're unlike the ones you saw up above. They use the word assign. Now the difference here is that assign, the keyword, when you use it like this, means that these 2 operands are tied together in a sense. For example, for D0, it says assign D0 to be the complement of big D. What this means is whenever big D changes, the value of D0 should change accordingly. In other words, the complement of D should be assigned to it. And again, this is what we call a continuous assignment. Whenever the value of the right-hand operand changes, the value of the left-hand operand has to change accordingly. Now beneath that is a for loop. This for loop is where the table that's going to get generated to the screen is actually produced. And really the purpose of this for loop is to go through my 3 bit streams, apply them to the mux, and then show in a table form the output. Note here in the for loop, I set up A, B, and C to be particular values in the bit stream. I then set the selection bits to be A, B, and C. And by doing that, it changes the selection bits for the multiplexer. Now here, in this if-else, I'm setting big D to be either 0 or 1 based on whether it's an even value of J or an odd value of J. By doing this, I'm changing the data bits. Remember up above the assign. The assign statements tie together the data bits D0 through D7 with particular values of D, or for some of them, just 0. So anytime D changes, big D changes, the data bits will change accordingly. There's a slight delay in here of 10 time units. And then this last line here, my for loop, the $display, which uses a C-style syntax, is actually going to produce to the screen, to the console window below, the value of the selection bits, as well as the value of big D, and ultimately the value of F, the value that the multiplexer is producing. And in this way I can generate a table of values that I can use to see if the MUX is working correctly. So what I'm going to do is simulate this model. Okay, so let's check it out. Let's simulate our behavioral model. When we do this, of course it goes through and it checks our syntax. However, when we simulate the behavioral model, you get some feedback in the console window, and ultimately your simulation window will pop up. And that can be useful for a variety of things, but sometimes it's easier just to print out a little table to the console window. So, if we look at what we have in the console window, the $display command in my test bench code is what produces this table you see here after finished circuit initialization process. I've listed on the left a simple counter value, 0, 1, 2, 3, and so on, going down the page. Then a colon, then a space, and then the 3-bit values for the selection bits. Then the value of D, and then the value of F, which is the MUX output. Now, what you could generate from, or what you could do from this, I should say, is verify that your multiplexer is working as expected. In other words, how it was designed. Now, in order to do that, you'd have to go back and look at the Mux8x1 code, as well as the values in the test bench that I used for D. And you could compare that and make sure that it is working correctly, or at least according to design. In this case, it is working according to the original design. And you can use things like this to help give you a quick and dirty idea of whether things are working. Now that said, sometimes it involves a lot of setup, but as a test bench, it's one way in which you can find that out. This is just another tool in the toolbox you can use.